Most of the audience are in the room, but I'm not there. I might delegate this job because I'm not normally going to be in Toronto on Fridays. But anyway, for now, this is the Fields Institute Postdoctoral Fellows Colloquium. And the goal of this is to take all of the postdocs who are here for the year or for the semester and provide a I mean, you're all working in very different fields of mathematics, but I like to make the opportunity for you all to get to know each other and talk to each other about mathematics and just have a sense of what everybody else is doing. And I'm hoping that this will be possibly just an opportunity to learn about some different kinds of mathematics and just have an enjoyable time, an enjoyable intellectual time. And maybe this will spark connections between different areas, or maybe you'll just have a good time listening for an hour to learn about what other people are doing. And because everybody's working in such very different areas, I hope that everyone will make an effort, that the speaker will make an effort to be communicating what they're doing, and that the audience will be making an effort to make sure that they tell the speaker when they don't understand, because it's always very hard. You have very good intentions, you stand up at the board and you say something which to you is completely obvious, and you just forget that it's not obvious to the rest of your audience. And so rather than just getting impatient or bored with our speaker, to actually just let them know that, hey, we didn't understand that. Could you explain it, please? So I really would like everybody to kind of feel like it's their responsibility to get something out of this by letting the speaker know when they don't understand something. So those of you who are actually in the room, you're the ones who really have the chance to kind of wave your hand at Jiayin and say, hey, we didn't get that. Can you just say something? And there we go. Brian's giving us a microphone so that you can say something, and us people who are zooming in can hear from a distance as well. I don't think that Jiayin can read the chat. So for the people who are in the Zoom audience, you're going to have to speak up if you want to ask a question. So just kind of keep that in mind. So, okay, so we're planning to meet every other week. And we have Jiayin today, who's a Fields Institute postdoctoral fellow. And just for advertising, 2 weeks from now, Margaret Nichols will be our next speaker. But for the moment, Jiayin, please go ahead and tell us about an invitation to Gromov-Hausdorff Convergence.
Okay, thanks for the invitation. It's my great pleasure to give a talk here. And I can't remember when's the last time I do a talk in a room. We've been online for a long time, right? So today I'll talk about Gromov-Hausdorff convergence. And hopefully this will be a friendly invitation so that most of you can understand most of the part what's happening here. All right. So in a nutshell, so without saying what's the actual definition, so let's say what's the meaning of, say, Gromov-Hausdorff distance. So Gromov-Hausdorff distance is a distance function defined onto compact metric spaces. I didn't say compact here, but I'll say later. So metric spaces. And when we say their Gromov-Hausdorff distance are very small, this means these two spaces, they look really alike. So you cannot tell the difference from one from the other. So when you have a sequence of metric spaces, Xi, Gromov-Hausdorff converges to some limit metric space, say capital Y. So we usually written as that way. That means it becomes almost impossible to distinguish Y and Xi for all I large. So that's the intuition. So now we're going to see some very simple examples. And I hope we can understand these examples without saying what's the actual definition of Gromov-Hausdorff distance. All right. So the first one is you can modify the Riemannian metric. So this Gi means a Riemannian metric on a sphere, and it converges to a foldable sphere. So let's say we start with the standard unit sphere, right? And next, I'm gonna make it a little bit longer and make the curvature at the north pole and the south pole a little bit larger. So gradually you change from this guy to this guy. Then you keep doing this and make these 2 points, the curvature there sharper and sharper. And eventually it will go to something like this. It's affordable, right? In the American sense, or something like this. So the point here is in the limit, it's no longer a Riemannian metric because you don't have smooth matrix defined on these 2 tips, right? Okay, so the second example is you can have a cylinder, a flat cylinder. Flat means curvature is always 0, converges to a line. So this is a very simple to visualize. So you have a cylinder like this, then you make the circle factor smaller and smaller. You shrink the circle factor. Now eventually this circle factor becomes smaller and smaller, and you can no longer see it, right? So it just disappears. So it converges to a line, all right? And the third one is a flat torus to a point. It's the same story, you just shrink that, right? So for any closed manifold, actually, you can always shrink it to a point, right? You just blow it down and it converges to a point. But the extra point here is for the flat torus case, you can keep in the curvature as 0 in this process. While if I say I shrink this sphere to a point, I can do that. But the curvature does not have an upper bound, right? When I shrink this, it becomes smaller and smaller, but the curvature will become larger and larger in this process. That's different from the flat torus case.
Could you draw a picture of a flat torus? Could you draw a picture? Could you just draw a picture of a flat torus? I don't know what that is.
I can't do that on the board because usually it's in R4.
Oh, okay.
So you take a circle in R2, then you do a product with another circle in R2. So it is in R4, so I cannot draw it. That's why I didn't draw it. If you draw the usual torus in R3, that's not flat.
So what makes it flat?
It's a metric product, then it's flat. I mean, one circle factor is independent of the other. So that makes it a curvature 0.
I see, sort of.
Okay, so next one is curve the surface to a tangent plane. So let's just, again, take this sphere, it's a curved surface. Now, instead of shrink it, blow it down, we fix a point, any point is fine, then you blow it up. You can think of you're using a magnifier and take a closer and a closer look at what's happening around the P, right? Then as this process goes on indefinitely, eventually you won't see everything, you won't see the circle, you won't see the sphere. You only see locally what's happening at P, and it actually becomes the tangent plane at that point. So maybe an easier way to expand this is you can have a curve inside R2, right? But this is not a good example. And if you draw a point and you look locally, then you zoom in, then eventually you just see a straight line. You just see the tangent line instead of the curved stuff, right? So the last example is integers to a line. So the last one is a discrete object. So that's the set of integers, say z, and you define a metric on this. Say the distance between k and air is absolute value of k minus air. So that's a distance function on a set of integers. Then you do a blow down. So you're zooming out. So in this process, these 2 adjacent points will become, yes. Yeah, sure.
Do you take into account the fact that the point could be singular, the nature, the algebraic nature or the analytic nature of the point in your geometrical object?
Yeah, there could be singularity arise, but right now for everything in the sequence, I'm considering smooth things. So you don't have singularity on the sequence, but you may have extra singularity arise in the limit, right? Okay, so let's go back to the Z example, right? When you blow it down, these 2 adjacent points become closer and closer, and you can imagine these points become in some sense denser and denser on a line, then eventually it goes to a line. It just filled it up, everything. So okay, so that's intuition. So you may ask, okay, why bother, right? So these things looks okay, but why we need this kind of thing? So the answer is sometimes to understand some nice spaces. Here, nice means, for example, a Riemannian manifold. You have a smooth structure on it. You have a smooth metric. To understand these nice spaces, sometimes we need to understand some singular spaces first. Here, singular means the one in the limit, where you may have singularity arise. All right. An analog in differential equation maybe is sometimes we want to understand the smooth solution of some differential equation. But to do that, we have to understand some weak solution. These weak solutions may not be differentiable at all, right? But by understanding these, it actually provides a way to understand the smooth solutions better. Okay, a note on the history. So according to Wikipedia, the GH distance was introduced by David Edwards in 1975, and it was later rediscovered and generalized by Michel Gromov in 1981. So I think it's really Gromov find its application in geometry, right? Okay, so now let's take a look at the actual definition. So this is the Hausdorff distance, all right? So you start with a metric space and the two subsets, X and Y are two non-empty compact subsets of Z. Then the Hausdorff distance is, so let me again draw a picture. So let's say you have a segment here and you have another segment here, all right? So this BRY just means you draw our neighborhood around Y, because there's a metric space, you can talk about distance, right? So when you draw a neighborhood, this is X, this will be BRX, right? So you find the smallest R so that X is contained in the R neighborhood of Y, and Y is contained in the R neighborhood of X. That's the Hausdorff distance. And it turns out that this actually defines a distance function on a set of all non-empty compact subsets of Z. So in particular, if you have X and Y, their Hausdorff distance are 0, then they are the same subset, all right? And additionally, if Z is complete, so recall that complete means every Cauchy sequence is convergent, right? It has a limit there. Then this new metric defined on a set of non-empty compact subsets, this is also a complete metric. Okay, so that is the Hausdorff distance. So Gromov-Hausdorff distance is about how you forget about the ambient space. So recall that we want to have a distance measures how two metric spaces looks alike, right? Let's say we have these two chalks. They're almost identical to me, right? But if I consider these two chalks as subsets in this room, then their Hausdorff distance could be large, right? Because Hausdorff distance depends on where this subset is positioned. You need to draw our neighborhood to include the other one, right? But they still looks identical to me, right? So the ambient space is not that important. Even if I ship this chalk to the other side of the plane net, it's still the same chalk, right? Assuming it's not broken along the way. Okay, so my point here is we need to forget about the ambient space. How to forget about the ambient space is you take the infimal among all ambient spaces, right? So this is the definition of Gromov-Hausdorff distance. You start with two compact metric spaces, then you consider all the isometric embeddings. So you embed this X and Y to another space, Z, while keeping the distance function. So isometric embedding just means all the distance are preserved, right? So then you can consider the Hausdorff distance between these two images in this new ambient space Z. Then you take the infimal of all these embeddings and all these metric spaces. So that's the Gromov-Hausdorff distance. And when we say xi converges to y, it just means the Gromov-Hausdorff distance goes to 0, right? And in some facts, if you have Gromov-Hausdorff distance between x and y being 0, that happens if and only if x is isometric to y. And secondly, if you take the isometry classes of all compact metric spaces, then this DGH defines a complete metric space on that, right? And for non-compact spaces, because so far we are talking about compact ones. For non-compact ones, we can talk about pointed Gromov-Hausdorff convergence. Well, you still need some condition like locally compact, but that's reasonable. So this xi will be a reference point. So we say that capital Xi, small xi converges to capital Y, small y, if for any ball, so this is the closed ball around the point, around your reference point. So this is a compact space because I'm assuming locally compact, right? If this is as compact spaces converges to the arbor in the limit, right?
So could you just go back a little bit? Sorry, Jiayin, just to say, so you're taking this, I mean, you're defining this function d sub gh, and it's defined on what domain?
It's defined on this MET sub C. You can define this on the set of all compact metric spaces modular by isometry classes.
Is that a set?
Yeah, that's a set actually. So the thing is you cannot say the set of all sets, right? But you can say the set of all metric spaces or the set of all groups. That's actually fine.
So my question is, do we know what MET C is? Is it except for that it is a set?
Well, it's a complete metric space. It's actually separable. You do have some other conditions, other properties of this. But okay, one thing I want to point out here, for most of the time, we don't care about the actual distance between two spaces. We only care whether the distance is small or not small. That's what we care. Maybe a better way to say it is that we only care when the convergence happens, right? So like if I draw a circle and I draw a segment and I say, okay, what's the actual, maybe segment is doable. Let's say I draw a circle and I draw a star, right? Then what's the actual Gromov-Hausdorff distance between them? It's very hard to calculate. And I don't think anyone cares, right? Okay.
Yeah, because it does seem like that you would have, I mean, you take, as you said in your example, you take two arbitrary compact metric spaces, X and Y, and to even know that there is some Z in which they both embed isometrically, it's like, do we even know that?
Yeah, because, well, Gromov-Hausdorff distance is taken as the infimor, right? So this will be very hard to calculate if you do want to calculate that. But anyway, most of the time we only care about a convergence actually.
So then we've got some particular set of or sequence of metric spaces for which we do indeed know that we can make sense of this concept.
Yes,
and then we ask whether it goes to 0.
Yes. Okay. So one question is how to make use of this concept, right? So in the worst case, if you have a sequence, but it does not converge, right? And it may not even have any convergent subsequences, then this kind of convergence will make no use at all. So the wish list here is we can have certain kind of pre-compactness. Pre-compactness means under certain conditions, whenever you have a sequence, then you have a convergent subsequence, and you can make use of this kind of convergence, right? So the wish list that we need to have certain kind of pre-compactness. I'm going to talk about when we do have that in the next slide. But let's say we have that, then we can pass to a subsequence, right? Then it will converge. And we can use this kind of convergence to study, for example, a family of metric spaces, right? You take a sequence, then you know it has a subsequence converge, right? Then you got a limit. And you can use this to study the infinitesimal structure of a metric space at a point. So say you have a fixed metric space X, then you take a sequence I to infinity, you do a blow up. So it's like Okay, I erased that. So it's like the tangent plane, right? So in general, this is called a tangent cone. And we can also use that to study the large structure of a non-compact metric space at infinity. How to do that? You can do a blow down, right? Like I didn't erase this. Like the cylinder, when you blow it down, this circle shrinks to nothing. Then it's a line, right? Or you can say this Z with this discrete metric. Then when you blow it down, it becomes a line. Okay, so now I need to address the question when we have a convergent subsequence. So this is proved by Gromov. So let Xi be a sequence of compact metric spaces. The sequence has a convergent GH subsequence if it satisfies the following two conditions. So the first one says its diameter has a uniform upper bound. So this condition is not that important actually. If it goes to infinity, then you can consider the pointed convergence instead, right? So the important one is actually the second one. It's called the uniformly bounded covering. So for any epsilon, we find a covering of Xi by epsilon balls. So epsilon balls means balls of radius epsilon, right? So the second condition says there is a uniform upper bound on the number of these balls. Okay, you can find a covering of Q many epsilon balls so that this Xi is covered, and this Q is independent of I. As an example, let me give you a sequence that does not have any convergent subsequence. So you start with a common point, so let's say P, and then you attach segments of, say, length 1 to that, right? So that this is your X1, X2 will be like this. So you have two segments attached to that. X3 is like this, and you do this indefinitely. And the one thing I want to point out here is the distance between two endpoints here is 2, right? Because you have to go back to the your common point, and then you go here. So it looks like when I draw it here, it's not 2, it's smaller, right? Because I'm drawing this on a blackboard. It's a 2-dimensional thing, but actually it has distance 2. And then now you do this indefinitely, then eventually it does not converge to anything actually. And it does not satisfy the uniformly bounded covering condition. Because so let's say you take epsilon equals to 1/2, right? Then how many balls you need to cover this? Then to cover every endpoint, you cannot cover every other endpoint. So for Xi, you have to use I many 1/2 balls. So you won't have a uniform upper bound there. Okay. So this is a good condition, but to make it more sense, why we want to make sure that it fits some nice geometric objects that we care about. So here are some geometric objects that satisfies the second condition there. Finite generated groups with controlled growth, and the Riemannian manifolds with rich curvature bounded below. So I'll talk about Gromov's work here. So I'm not presenting his proof. I'm just talking about his innovation there. So a little bit background. So let's say gamma is a finitely generated group, right? And you take a finite generating set, say capital S. Then you can naturally define a so-called word metric on that. So the distance between E and gamma is just, now recall that S is generating set, right? So any element gamma can be written as a word in S. Then you just count how many elements you used, right? For example, if you have gamma is Z, so that's the set of integers, and you take the generating set as, say, 1, right? Then the distance between 0 and K is just a K, because you need to write K as 1 + 1 + 1 K times, right? But you can also take other generating set. For example, you can take 2 and 3. It's not efficient, but that's still a generating set, right? Then the distance between 0 and 1 is actually 2. So I need to point out this distance depends on the generating set, right? Because you have to write 1 as 3 minus 2, 2, right? So you use the two words. 1 is 3, 1 is 2, right? Okay, so then there's the growth function. It should be goes to the next line, but anyway. So growth function just means you count how many elements in that ball. So I forgot to say that line, this line, ds. I can go to last slide, right? The distance between gamma and gamma prime, you just do a left translation. And that defines a left invariant metric on this finitely generated group, right? Okay, growth function is just you count how many elements is in the ball of size R, right? So that's GSR. Well, for example, this one, right? How many elements distance less than k? That's just 2k plus 1, right? Because you have negative k to 0 to k. That's 2k plus 1 many elements. And we say gamma has polynomial growth if the growth function is controlled by a polynomial. It turns out that this definition is independent of the choice of s. So although the distance function may depend, right, like what we see here, you pick a different generating set, you may end in different distance function. But you can see the asymptotic behavior of this growth function that really didn't depend on the generating set, right? Some examples like Z has polynomial growth and of degree 1 actually. Then if you have Z to the K, that has polynomial growth of Z to the K actually. And if you take a free group means you have no relation at all, right? You generate it by AB, then you can write AB, AB, AB. That actually does not have polynomial growth. It has exponential growth, right? How many elements can be written, say, with word length K? That's 2 to the K. So it does not have polynomial growth. So lastly, if gamma has a subgroup of finite index, say H, then gamma and H have the same growth type. So if two groups, they only differ by a finite index, then it didn't matter, all right? Okay, so we know abelian groups, right? So I'm saying nilpotent ones because I'm not presenting Gromov's proof, but I need to present his statement, right? So to present a statement, I need to say what are nilpotent groups. So we all know abelian groups, right? Abelian groups means it's commutative. So this gamma means you take all the elements, looks like G inverse H inverse GH. So that's usually written as this, the commutator. Then you take all these commutators to generate a subgroup. That's that gamma, all right? So abelian just means you take the commutator, you get identity, right? Nilpotent ones are the next best thing. You take commutator, it's not identity, so we write as subgroup, say gamma 1. Then you do this inductively. You call gamma I plus 1 as the commutator between gamma and gamma I. Then eventually you reach identity. So that's nilpotent. A very simple example is this discrete Hessenberg group. You take all the 3 by 3 matrices, upper triangular ones, and they're one on the diagonal, and ABC as integers. If you take the commutator, it's just like how you calculate matrix multiplication. If you take the commutator, the subdiagonal will become 0, and only the top corner is a C there. Then if you do the commutator again, that C also disappears. So this will be a classical example of a nilpotent group. And it's proved by Wolff in 1969 that any finite generated nilpotent group actually has polynomial growth. So I write virtually here. Virtually just means it contains a nilpotent group of finite index. So in the last slide, we talked about a finite index really didn't change the growth type. So I can state here, any finite generated virtually nilpotent group has polynomial growth, right? So Gromov solved the converse of this. So if you have, say, a finite generated group of polynomial growth, is it virtually nilpotent? So that's what Gromov proved in 1981. So the novel part in Gromov's approach is you consider this metric that we talk about, and you do a blow down. So you take any sequence I to infinity. If the group has polynomial growth, then this blowdown sequence actually is pretty compact in Gromov-Hausdorff topology. In other words, you can have a limit metric space. So after passing to a subsequence, you can have a limit metric space, say G, with a distance function d there, right? Then Gromov used this limit space to prove the theorem. I'm not talking about more details, but that's the novel part in his proof, right?
Is the limit space still a group?
Yeah, it is a group. Actually, it is a group.
So it's not obvious that it should be. I mean, not in, or is it obvious?
It's kind of obvious that yeah, but I can tell it. This is well studied. So the structure. Okay. So then I'm gonna say a little bit more in the next slide, mm-hmm. Right? So let me show you a few simple examples, like Z, right? You take, so this is the example here. I still didn't erase that. This is the Z with the metric. So that's exactly the word metric. And you do a blowdown, it goes to a line, right? And you can also do Z2. Z2, let's take the easiest generator, 1, 0, and 0, 1. It's rarely you have discrete things over there. Okay, so these two will be your generators. So if you have a point, say K air, right? In Z2. So let's call this gamma. So the distance between identity and gamma will be K plus air. I mean, the word metric. So when you blow it down, you didn't converge to the standard metric on the Euclidean plane. You actually goes to the so-called box metric. Right? Box metric means if you have a point here, what's the distance between, say this point is AB. What's the distance to the origin is absolute value of A plus absolute value of B. So that's the box metric. So you go this way. Then later, Pan-Su give a very detailed description of what's this G. This G is actually a simply connected Newpolton group. And what's the distance D there. And it actually also leads to the study of so-called sub-Riemannian and sub-Finitely metric. So I'm not talking more about this, just give you an idea that it leads to some kind of new field. Okay, so that's the story of finite generator groups. So next I'll talk about the other application. They're actually much more than finite generator groups, is on Riemannian manifolds. So recall that we have that uniform covering condition, right? So it turns out that if your sequence has this uniform Ricci curvature bounded from below, then it automatically satisfies that condition. So if you're not familiar with Ricci curvature, so you may ask, so what's the point of this negative n-1? Why there? It's because Ricci curvature is the sum of n-1 many terms. Usually we're doing a renormalization so that the lower bound becomes this. But you can put any number there. That didn't matter. Okay, you can replace that negative n-1 by your favorite number. It didn't change the statement. Okay, so Gromov-Hausdorff convergence, because now you always have this pre-compactness, so it provides a platform to study a class of Riemannian manifolds with uniform geometric conditions. For example, you can consider sectional curvature two-side bounds, or sectional curvature just lower bound, Ricci curvature two-side bounds, or Ricci curvature lower bound. And then another condition that come up usually is the volume condition. We ask whether the volume is away from 0 or it goes to 0, right? If it's away from 0, this is usually called the non-collapsing case. If it goes to 0, this is the non-collapsing. For example, if you're shrinking this cylinder to the line, that's the collapsing case, right? The first example, like the spheres goes to a football, that is non-collapsing. So intuitively, in the collapsing case, the limit space will have lower dimension, right? While the non-collapsing should have the same dimension. So some questions to be addressed is, what can we say in general about the structure of the limit space? And what can we say about the relation between x and all mi large? Now, some of the properties can be passed to the limit easily. For example, X is indeed a length metric space of Hausdorff dimension at most n. This is always true. Here, your sequence of manifolds reach curvature bounded below, right? But in general, the limit space could be very bad. It may not be a manifold. It may not be locally contractible. And it may not even have integer Hausdorff dimension. So it could be pretty bad, right? So the best case is we have something called the stability. So that happens usually, well, you need that, it's not usually. That happens only when it's non-collapsing. So you have a volume lower bound. In other words, the limit will more or less have the same dimension. Under certain curvature conditions, this limit is indeed a manifold. It's indeed a manifold that is diffeomorphic or homeomorphic, depending on your curvature conditions, to mi for all large. In some cases, you may even have a Riemannian metric on the limit space X, and you can talk about certain convergence of Riemannian metrics, right? So that's the best case. It's called stability. One consequence of this stability is you have finiteness. Finiteness means you only have finitely many types of diffeomorphism types or homomorphism types. So this is the argument I can actually present. So suppose not. Let's say you want to show a class of Riemannian manifolds with certain curvature conditions only have finitely many diffeomorphism types, right? So the argument goes like this. Suppose not. You take a sequence of mutually distinct mi, then you can take a convergent subsequence because you have free compactness. Now, if you have that kind of stability, then for all mi large, it's diffeomorphic to X, right? So they won't be mutually distinct. That's a contradiction, right? So that's a very simple argument. So some of the results that falls into this category, the first one by Chigger, if you have sectional curvature uniformly bounded and the diameter upper bound and the volume lower bound. So you take all these manifolds with this condition, and there are actually only finitely many diffeomorphism types of these manifolds, right? And if you remove the sectional curvature upper bound, you only assume a sectional lower bound. That's proved by Pellman. You only have finitely many homomorphism types. The last one is a more recent one compared to the previous two, and it's actually much harder. So collection of closed form manifolds with reach curvature, two sides bound, and the diameter upper bound, volume lower bound has finitely many diffeomorphism time. The difficulty of the last one is the limit may not be a manifold. The limit is not a manifold. So what they did is you need to show that there are some bad points there, but these bad points are controlled, and you don't have too many bad points. Then you can still extract a finiteness out of that. So general limit spaces, right? And the last slide is the non-collapsing case. General limit spaces. So sectional curvature side, both side bounds, these are well studied. So these are actually orbit space. Orbit space means some space modular by a group action. You take the quotient, that's the orbit space. Then sectional curvature, a lower bound, that's usually called an Alexandrov space. Then reach curvature lower bound, we just call it reach limit space. And this also leads to the study of non-smooth metric space with synthetic curvature conditions. This means you just kind of forget about the sequence. Let's say I have a general non-smooth. Non-smooth means it's not a manifold metric space. And what can we say about its curvature? Can we put a reasonable curvature lower bound condition on these non-smooth metric spaces, right? Okay. So in contrast to the non-collapsing case, the other extremal side is so-called maximally collapsed. Maximally collapsed means it goes to a point, right? It's like the example we see. We can shrink a torus, a flat torus, to a point. We can also shrink a sphere to a point. But the difference is, for the torus, you are keeping the curvature 0. For the sphere, you have curvature upper bound that goes to infinity, right? So here, and you can take M as the same manifold without losing generality. Anyway, so we ask what kind of manifolds can converge to a single point while keeping the curvature bounds. So for example, any closed flat manifold, you can plot it down, it goes to a point, and the curvature is always 0, right? Almost flat means you keep the curvature bounded by 1. Almost non-negative means bounded from below. And then almost non-negative Ricci just means you have Ricci curvature lower bound. So a question you may have is, isn't almost flat make more sense to say sectional curvature is very close to 0? That's actually true because it's a rescaling argument. So the original metric goes to a point. If you rescale by the diameter, you can say I keeping the diameter as 1, but the sectional curvature goes to 0. Because when you scale it up, the curvature becomes flatter, right? The curvature becomes closer to 0. So that's why it's called almost flat. So an observation is any closed manifold, if you take a closed flat manifold, topologically, it's finitely covered by a torus. This means you can take a finite cover and it's a torus, right? So for almost flat or almost blah, 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 these manifolds are well understood in some sense. Like Gromov showed that almost flat is finitely covered by a new manifold. So new manifold means it's a simply connected nilpotent manifold modular by a lattice. So just like torus is RK modular by ZK, right? It's a simply connected abelian group, Lie group, modular by a lattice. So new manifold is a simply connected nilpotent manifold modular a lattice. Then the next two conditions are about almost non-negative sectional curvature and almost non-negative Ricci. I'm not gonna define what is a nilpotent space. I'll say a little bit of words on CN nilpotent. CN nilpotent means it contains a nilpotent group of index at most Cn, right? So it's virtually nilpotent, but we also have a control on how virtually it is, right? What's the index of that subgroup? Now, some selected results derived from this collapsing theory. I'm not talking about any technical details. I'm giving you a sense what can be achieved with Gromov-Hausdorff convergence. So this is a result by Rome. Closed manifolds, unmanifolds with positive sectional curvature bounded between a delta and a 1. So this is usually called a delta pinched condition. So then the fundamental group has a cyclic subgroup of index at most Cn delta. So this kind of fundamental group is always finite, actually. So cyclic is really a finite cyclic group, right? So by the way, he's my PhD advisor, and he's a nice guy. So next, this is proved independently by Petrunin-Tushman and von Rome. So the collection of closed manifolds, you assume pi1 and pi2 are trivial. And the sectional curvature bounded by 1 diameter upper bound has only finite many diffeomorphism types. So this is very different from the stability case. In that case, you have a volume lower bound. This one does not. So the limit could be a lower dimensional thing, and you don't have stability at all. So you do need a deeper understanding of the collapsing theory to prove something like this, right? And you do need the conditions over there, pi1, pi2 are 0. Then the next one is proved by Carpuch-Wilkin. If you consider closed N manifolds, Ricci curvature lower bound and diameter upper bound, then you can have a uniform control on the number of generators of the fundamental groups. It has at most some C and D. Oh, by the way, all of these constants are implicit. So they're not explicit constant. I cannot write it down. So the argument will go like, suppose you don't have an upper bound. you have more and more generators, then you can have a subsequence convergence in Gromov-Hausdorff, right? Then you have a limit space. Then you find a contradiction somewhere. So the argument always goes like this. So you don't have an explicit expression of these constants, right? Okay, lastly, it's my talk, so it's reasonable to include one of my results here. So there's an alternative proof of the Minimal conjecture in dimension 3. So Minimal conjecture says open and manifold of non-negative rich curvature always have a finitely generated fundamental group. So this result is first proved by Liu in 2013 using the minimal surface theory and also Pellman's solution of the Poincaré conjecture. So the alternative proof I presented does not use this kind of thing, only use Gromov-Hausdorff convergence and the structure of limit spaces, right? So again, I'm not praising any actual details of the proof. I'm just give you a sense what can be done with this platform. And most of the thing I presented here is almost unthinkable without the language of Gromov-Hausdorff convergence, but their statement has nothing to do with Gromov-Hausdorff convergence at all, right? I can present all of these statements without mentioning what is Gromov-Hausdorff distance, and even Gromov's original work, right? Polynomial growth means virtually nilpotent. It sounds nothing to do with metric spaces. It sounds nothing to do with Gromov-Hausdorff distance. But the proof is you need to go there, right? Okay, so that's all of my talk. Maybe I'm running out of time already. Oh, I'm within time. Okay.
That was perfect. Thank you very much.
Okay, questions.
Yeah, yeah, Jiayin, that was a great talk.
10 minutes for questions.
Any questions from
there
Leo?
are still many open questions in this field. Like the first result there, it's open whether you can drop the dependence on delta. Let's say you have positive sectional curvature, then whether the fundamental group is CN cyclic. And for example, the minimal conjecture in general, right, in dimension n. So these are very hard questions, actually.
Well, I'm going to show something I don't know. Are there Milnor conjectures in other dimension?
Yeah. So the minimal conjecture is in general dimension n. And we don't know what happens for dimension greater or equal than 4. There are some partial results, yeah.
Do you think that you might be able to approach it with with your way of looking at it?
Yeah, so the idea is, actually I mentioned it somewhere, is you do a blow down, right? It's similar to Gromov's approach. So somehow you blow it, I go too far away. Like here, you can do a blow down, but it's not doing blow down on the base manifold. It's you do that on the universal covering, because on the universal covering you have the information of the fundamental group carried, right? And another thing maybe I can point out is in this Gromov-Hausdorff convergence, most of the time you can carry other information along, right? You can say, I have functions on xi, I have measures on xi, I have group actions on xi. Then under some conditions, these things can be carried to the limit as well. Then you can study these structures, use this platform. Yes.
So since you said that, I guess, is there any way to see this with alpha products or?
There is, so you're saying some, would you say that again? Sorry.
Alpha products, because I know the Gromov proof of the important can go through with alpha products. So I was wondering if the general Gromov-Hausdorff convergence could be seen like that.
Okay, I understand your question, but I'm not sure the answer. Because what I'm familiar with is more the geometric side. So I'm not familiar with the ultra product. That's an algebraic construction, right?
But I think that is a good thought for the model theorists, because it does look to me, and certainly there's been some work on the word distance in groups using continuous model theory. And that would be really nice thing to know whether you could do more, whether you could use continuous model theory for more of these questions.
Yeah, later on, I mean, people find other ways to present Gromov's proof without this kind of language by using some algebraic construction, right? But I would say this is the one I'm familiar with and I'm comfortable with. Depends on your field and preference. Yes.
And then the same thing for y prime. Y and y prime agree almost everywhere in the sense of the original metric at y of the space y is in. These distances, that distance shouldn't a priori be the same as dgh, would it?
Sorry, I don't quite get your question.
Like if you allow, if you sort of ignore, you know, what's happening on null sets where null in the sense of the original metric, do you get the same dgh like when you implement?
So I mean, here x and y, you don't start with any ambient space at all, right?
Oh, so they don't have metrics on them?
They have metrics.
Okay.
They have metrics.
Yeah, that's what I mean. So if in the metric on x and the metric on y, you are allowed to pass the subsets that agree with x and y off of a null set. Does the
Oh, you're saying their distance, like they agree almost everywhere?
Exactly, right. Is it the same metric?
So first of all, they cannot agree almost everywhere, but not everywhere, because distance function is a continuous function. Maybe I shouldn't say that. It could be not. It could be not. Okay. So, but to address your question, there is a there is another concept. So like if you consider a ball, right, and you attach a very thin stuff to that, right, a very thin long stuff to it. If you take the Gromov-Hausdorff convergence, so you say this becomes thinner and thinner, but still take out this way, right? If the Gromov-Hausdorff convergence will converge something like this, right? But there is another concept. You can ignore some measure zero stuff. So, but it's different from Gromov-Hausdorff convergence. Another concept of convergence that will converge to an actual sphere with that ignored. So in general, if you do have a measure zero or goes to zero, the Gromov-Hausdorff distance could be different. But there also another concept says you can ignore these.
Okay, yeah, I wondered.
Yeah.
Any other questions from the audience?
I got a small question. Can you hear me?
Yes, I can hear you.
I was wondering, because you were giving these examples about the sphere, and I noticed, so this would be metric spaces that are definable in, for example, the field of reals, right?
Sorry, I didn't get that part.
When you're talking about these examples that you're drawing on the board, these would be spaces that are definable in the field of reals.
Jiayin probably doesn't know what definable means, Pablo.
All right. Sorry. That's fine. Yeah, I was just trying to reconcile, like I was trying to understand like what's the interface between model theory and these results. But I think the way you said it is, it's usually you're not considering all these spaces, say all these groups or all these manifolds inside one structure or one ambient space.
I mean, I think that that would actually be a question for a model theorist to look at, is to say, can you kind of put, if you did make that assumption, you start with a sequence of metric spaces, all of which are definable over the reals, and then, I mean, I think probably you could say the limit was probably still definable. That would be like one thing. I think that's probably
right. Okay.
But,
yeah. Okay. I was just wondering, like, to what extent, if you're in the case where you're working within a single structure, like with the examples, to what extent you can use, say, the tame geometry of that structure to try to talk about these kind of convergence results and so on. Yeah, that was it.
You're saying tangent structure or something?
Excuse me?
What kind of structure you just mentioned?
The field of reals I was saying before, because the examples you mentioned, they all seem to fit within, like, they are like Euclidean spaces. So I just thinking to what extent maybe the model theory of the field of reals, like, can play a role in trying to understand these metrics.
I think that's a question that has to be discussed over lunch.
Yeah.
So for Riemannian manifolds, you can always embed it into some higher dimension, R capital N, right?
Right.
And regarding the definition of this Gromov-Hausdorff convergence, actually, there's a alternative way, but equivalent way to define this is you don't take all the infimos, say, all over Z. You can just actually take the so-called disjoint union of X and Y. So you can take X as the disjoint union of X and Y, and then consider all the embeddings into this, that would be actually enough. It's just, it makes more sense to present it in that way, say, taking the infimo of all metric spaces.
Examples. All right, thank you.
I don't know whether that answers your question.
Okay, are there any other questions? Well, then let's thank Jiayin again for a very beautiful talk.
Thank you.